Hello, folks. Welcome to today's webinar on real-time recommendation systems brought to you by Aerospike. We're going to be talking today about how modern recommendation systems are designed and how they need a world-class database infra to power the machine learning inference, and how Aerospike plays that role across many customers such as Myntra, Sony, Wayfair, etc. Without further ado, let's get started. Here's the agenda for the day. What I'll be doing is I'll kind of sketch out how modern recommendation systems work or behave and give you a gentle introduction. Then we will have another gentle introduction to Aerospike, the real-time database. And then we'll put these two together, right? So why is Aerospike the best data infra for recommendations? And then we will hit upon some customer stories that sort of point to this repeatedly. That's the goal for the day. So let's talk about how modern recommendation systems look like. Before that, just to set the stage, all of you know that recommendations are the engine that basically drive relevance and engagement. This could be on an e-commerce website, or it could be on a gaming platform. It could be while you're watching, Netflix or Spotify or whatever else, or it could be while you're transacting, with your financial services provider, or it could be within the context of an ad tech system that's actually, publishing ads on sites such as the New York Times and so on and so forth. So there's a wide plethora of variety of situations where recommendations get used. In my opinion, recommendations is one of the broadest use cases that pretty much encompasses everything that you see in an online world. I call it the matching engine. Sometimes whenever you're matching two things, that's really a recommendation. You're sort of recommending that those two get matched. And those two things can be a user and a product, a user and a set of news stories, and so on and so forth, right? So any number of such combinations. And the key is that in today's world, we need to sort of engage users in the brief moments where they're ready to make decisions. And they're probably given some signals a few seconds before, a few milliseconds before. These are the real-time signals as part of that session that they are involved in. And then using these signals and other historic signals, we have to make split-second choices, and we have to do this millions of times per day. And this is what drives engagement, whether it be time spent on the site, whether it be CTR, or whether it be long clicks, whatever your metric is, whether it be add to cart, if you're an e-commerce website, or purchase. So whatever your measure of getting deeper into the user's consciences, if you will, right? So that's what recommendations are supposed to drive. They are the final business driver, if you will, for online websites. So I actually want to sort of frame the recommendation or how to think about recommendation in terms of a three-lens framework. And I find this very useful because many times people, while building recommendation systems, do not know how to trade these things off or do not know what to trade off for what. And just sort of stepping back and saying, hey, there are three very different things that need to come together to make a recommendation. The first thing is what's called the user request. Okay, so this is kind of, think of it as the current intent. Okay, now in many cases, this intent is very explicit. For example, if you're in a search engine or if you're in front of a chat bot, you're actually typing in a particular query or a particular prompt, if you will, right? So in that context, there is a very explicit user intent. But many times the user intent is implicit. You just landed on New York Times. You didn't say what ad you wanted, or you landed on Amazon.com. You're on a product detail page, looking for your favorite Levi Strauss jeans. You didn't say what other products should be recommended in that You didn't say that explicitly, right? So many times these recommendations are implicit. So in the search and the RAG context, they're explicit. In the recommendations context, it's implicit. So the request, if you will, in the recommendations case, is just what you did in this session. So it's kind of the intent that you kind of demonstrated in this session, right? User context, on the other hand, is a bit more historic. It's like, hey, what kind of a person am I? What brands do I like? What colors do I like? What price points do I like? What kind of news articles do I like? What kind of topics do I gravitate towards? So on and so forth. What genre of videos do I like? So that's the sort of the user context, right? And then there is something called a business context, which is really, bringing in the business logic which is, for example, if you're in an enterprise setting and you're building a, intranet search or what I'll call enterprise search, then who can access what is some kind of a business context that you bring. If the e-commerce setting, it could be what do the merchandisers want to promote right now? Is there a clearance sale going on some products? Or do we have to get rid of some things that are very old inventory and so on and so forth, right? And in the ads case, it might just be, hey, what is the build? I mean, how much is this advertiser willing to spend to show this ad? And that's at another context. And you have to juxtapose these three things, if you will, right? And that's how you make the recommendation. And usually a good rule of thumb is, obviously, for a good recommendation system, you want to make sure the user request is paramount because that is their current intent. And then you overlay their sort of history and business context. And obviously, if you can get the intersection of all three right in the middle there, that's great. Otherwise, yeah, you will have your own way of deciding how to fall back when only two of the three are right and only one of the three is right. So that's all part of what I'll call we'll later look at this, what we'll call the re-ranking phase, if you will. So with this, so I think going forward, it is important to remember that whenever we talk about a recommendation query, I'll call it a query just generically. What we really mean is this triplet, right? What is the request? What is the context? And what is the business context? Okay. So the way a recommendation system typically works is there is some kind of a recommendations funnel that gets created. So typically there are millions of choices or millions of candidates from which you can choose, what to recommend. And there is something called a retrieval phase. Now, this retrieval phase is usually built on top of, could be a vector-based retrieval, could be keyword search-based retrieval, could be simple structured search-based retrieval. For example, if you said, if you are interested in retrieving Nike shoes under $100 for women, that actually turns out to be a very structured query. The brand is Nike, the category is shoes, the price is less than 100, the gender for which this is applicable is women. So you can almost issue a structured search query. Anyway, however you do the retrieval, whether it's a structured search, keyword search, vector search, these are all what I'll call quick and cheap ways of restricting the millions to thousands of options. Then you might have what's called a filtering step where, various kinds of other things might have to be applied, such as whether is it in stock, is this something that they have already seen too often, blah, blah, blah. Okay. So there might be a bunch of filtering steps. We'll look at a few concrete examples later. That might whittle the thousands down to 100. And then finally, you apply usually a fairly sophisticated machine learning algorithm which is called re-ranking. And that takes those hundreds and brings it down to about tens. Notice that obviously you could have re-ranked on all the millions of at the same time and got the output, but that would have been tremendously expensive. So this funnel approach is kind of a way of saying, okay, I will apply a cheaper kind of a ranking function on larger data set, and then I'll apply my more expensive ranking function on the smaller data set. Okay. And then finally, we might decide to order these results in a slightly different fashion than just what the rankings suggest. And we'll look at an example. So the ordering is how you present it to your user. Okay. So let's look at some examples to sort of make these 4 stages concrete. Um, the first example is music discovery. I'm sure you've all used some kind of a discovery app or not. If music discovery, it could be YouTube, could be anything else, right? So what the recommendation engine typically does is if you're listening to something or watching a video, then it looks for similar songs or similar videos based on what's called a nearest neighbor search. Okay, and this nearest neighbor search, for example, could be performed with a vector retrieval. Then, we might remove tracks, users that you have listened to before, because it's, no point recommending the same thing again and again. Then the re-ranking phase says, here is what's the likelihood that the user will listen to your song. This is where you build a complex model and rank, the hundreds or so of choices that would come out of the filtering step. And then finally, let's say you have a few 5 to 10 options. You say, okay, it's all sorted on likelihood, but I also want to make sure that I'm presenting enough diversity. So it's not useful if I present the same genre of music or same kind of beats per minute or whatever, right? So you want some diversity, not the same, artists involved, same bands involved, and so on and so forth. So you want to create diversity, and that's sort of done that's the ordering step. Same example, similar thing for social media. How does Facebook or Instagram or others, how do they recommend new posts for you? Then again, so you'll find new posts that are in your user's network. You'll remove the posts that are blocked and muted in the filtering step. Again, that'll be a prediction, the re-ranking step, and then the ordering step will make sure you have diversity, different authors, different topics. And similarly with an online store, whatever your favorite e-commerce store is, right? So you're on a product detail page, find which items are usually co-purchased with the item. Of course, not that recommendations need not be only on a product detail page. They can be elsewhere. I've just taken this example. And then if you have to remove things that are out of stock in the filtering step, and in the re-ranking step, again, predict the likelihood that the user will actually purchase this item. And then you might say, okay, I'm going to reorder based on price points, as well as sometimes I want to encourage explore versus exploit, because machine learning models tend to get into a local minimum, and when they're constantly exploiting. So you want to encourage explore, right? But that's sort of recommendations at a very high level, okay? What I'm going to do next is to give you an introduction to Aerospike, and then we will tie Aerospike and recommendations together after that. Okay, switching gears dramatically, we're going to talk about Aerospike. Okay, why Aerospike for recommendations? Well, the most important reason is Aerospike is able to give you predictable latency at high throughput and reliability. And this has been borne out in sort of many situations where we power mission critical use cases and workloads, right? For example, for Sony, and Adobe, we power, for Adobe, for example, 20 terabytes of data on the edges and 10 petabytes of data in the core. So huge scale. And for Sony, 6 billion TPS or 8 million TPS at less than 10 millisecond latency. So predictable latency at high throughput. Also, we do this while keeping the total cost of ownership very low. For example, in Rakuten, we dramatically reduced the infrastructure cost by 80%. For Wayfair, we brought 60 Cassandra servers down to 7 Aerospike nodes, and so on and so forth. And finally, this is optimized for machine learning and AI, as this talk will demonstrate, right? So how Aerospike is optimized for recommendations. That's going to be the topic of this. And we will talk about Myntra in some detail. Now let's dig a bit into why Aerospike is so performant and what is the unique differentiation of Aerospike. So there have been typically 2 schools of thought. One school says, to get performance, you keep all your data in RAM, and yes, it will give you performance, but the cost is going to be pretty steep. The other group says, no, no, we got to keep the cost in control. So what we're going to do is we got to put the data on SSD and then some kind of aggressive caching and try to get the performance to a better stage. Okay. And so that group is down here in yellow. And the key sort of innovation within Aerospike is what we call the hybrid memory architecture. It's a patented architecture where we kind of are able to give the performance equivalent to databases that store data in RAM in terms of latency, while giving the cost of databases that store data on SSD. And that is well, there's sort of a lot of literature on how we do this, but that's the best of both worlds. So give the performance of as though things are in memory while storing them on disk and therefore incurring the cost of disk. Okay. The next thing that's sort of noticeable about Aerospike is its predictable low latency. And we will later see how this is super important for recommendations. But this picture, what it tries to convey is that, on the left, towards the left part of your screen, you see data stacks here where, there is substantial variation in the latency and the average latency is pretty high. Whereas when you come down to the right, the variation comes down dramatically. And not only that, the average also comes down. So this is why we say it's predictable low latency. So 99.99% of your things will finish in less than 1 millisecond. Such guarantees. And as we will see, tail latencies are super critical. Okay. And that's what Aerospike is able to give. And it does all this at the lowest cost of infra. For example, repeatedly, whether it's Adjust, TransUnion, and Criteo, we have actually reduced the infra size of the infra cost, usually by 60 to 80%. It's repeatedly something that we are able to do. And finally, and this is an important point for global organizations and global enterprises, is Aerospike has inbuilt asynchronous replication where it's able to take the record stored at a central hub or from a system of record, which could be Aerospike, or most of the time it is Aerospike, and then copy it or cache it at the edges. And this copying and caching is not a one-time copy; it's a continuous, stream of updates. So as the core changes, it streams those updates to the edge. And this uses something called XDR, which is again another of Aerospike's patented technologies, and it does this very efficiently without putting any load on the system of record. But then taking the data very close to where the user is. And latency is all about, honestly, the biggest sort of contributor to latency is network latency when people are very far away, when the user is very far away from the data center from which you are getting data. So in that sense, being able to take the data close to the user is super critical, and that's what Aerospike is able to do. Okay, so that was world's fastest introduction to Aerospike after a world's fastest introduction to recommendations. So now let's see how these two sort of come together, right? So why is Aerospike a good data infra for recommendations? Before we kind of get into that, let's sort of look at what I call a generic recommendations engine pipeline architecture. By generic, what I'm saying is most machine learning architectures have something, are very sort of isomorphic, if you will, to this. They look like this, and essentially, most machine learning architectures, they have what I will call a fast path and a slow path, or an offline path and a real-time path. And the real-time path is actually as people are interacting with the site, there are events that are flowing in that are ingested using Kafka or whatever pipeline. There's some stream ingestion that goes on. That in turn might sort of give you some features, or it may give you some state store or session store information. And that's what gets stored here. So it might be features directly or state or session stored. And that comes through the real-time path. And then the same data could also sort of get accumulated and come via a batch mode. Or there might be other data that's not related to user activity at all. This could be just the product catalog or the inventory, which these are all not directly related to the user catalog. User activity, and they come in and they are ingested in a batch mode, and then features are generated and stored in an offline storage. And then there is a machine learning sort of a model training that happens on that data, which might generate more features, right? So the model training might generate newer features or train features, if you will. And then there might be a newer model also that might be put into the inference step, okay? So now that's what happens as far as the data training and loading the inference engine. Now at the inference time, there is a user request that comes from the right, and then you sort of talk to the ML inference engine, which in turn might consult the state store or the session store or the feature store or even an inference cache. Maybe you made the same inference before, so why repeat that, right? So that could be an inference cache. So this is usually Aerospike. This is a sort of a multi-purpose data store in the context of real-time inferencing. We will double-click more on the feature store aspect of Aerospike in this talk, but like I said, it can be used for many other purposes in the real-time inferencing engine. And finally, the recommendations goes out to the user, right? Okay, so this is the generic architecture. Now, before I kind of tell you how Aerospike sort of addresses or how it's a good feature store, I actually want to sort of focus on this quote. This is from Sajjan Kedia, who is a data scientist at Myntra. And let me read it out, right? So he says, when we analyzed our recommendation pipeline, we saw that often more time was spent on feature lookup than on the actual model prediction. Now that's really sad, right? So if you're sort of, if you're saying you're a complex machine learning pipeline, but your database is taking more time than the machine learning inferencing part, then that's a challenge. And we will look at this example again, but you will kind of remember this quote again when I go through why it is the case that we can give back more of the time, more of the budget to the machine learning inferencing models, right? Why is it? Anyway, as a result of this, of course, they reduced from close to 10 milliseconds or 8.5 milliseconds to less than a millisecond, 0.8 millisecond. So now we're going to see why Aerospike is able to do this. Okay. Before we go there, what I'm going to motivate now is I'm going to motivate why does retrieval take so long from a database? Why is the database taking most of the time? Okay, why did they make that statement? And that statement is actually has its roots in two different problems. What we call the width and the depth, if you will, of retrieval. What that means is, on the one hand, there are multiple steps. We already saw the 4 steps, right? So we saw retrieval, we saw filtering, re-ranking, ordering, and so on and so forth. So there are multiple steps. And each step is typically sequential. So you got to, finish one step, then go to the next step, and then go to the next step. And typically each step requires consulting the database. That's part one. Part two is, as you create more and more complex models, or as you trade off the time for model with pre-computing more and more data and more features, if you will, you need more and more data. Not only do you have multiple steps, at each step you are going to need more data. So that is the fundamental problem that makes the database a choke point in these pipelines. Okay, and we're going to see how Aerospike solves for it. But to illustrate that sort of, I'm going to first talk about the multiple steps, and then we'll talk about the fact that we need more data in the next slide. Okay. So in this case, I've just picked up 2 steps, retrieval and re-ranking, from the 4 steps we had there. These are the more, I would say, intense of the four steps. So I picked on these two. And like before, obviously the original query, like I said, always consists of the striplet. What's the user request? What's the user context or personalization? And what is the business context, right? So take those three, you go retrieve from the candidate thousands or hundreds of documents and then re-rank them and then emit tens of documents. So there are multiple steps, uh, like we saw before. Now, although I kind of said re-ranking, I'm going to double click on that. So we have already established that there are multiple times we need to dip into the feature store. Now I'm going to talk about how much data are you going to need to get from the feature store for the re-ranking step. And I'm going to drive this through one example and then we will generalize it, okay? So this is a very concrete example. Let's assume you're doing recommendations in an e-commerce store. Then the products, all products have a title, they have a description, they have some other textual attributes. And so standard text models, text similarity models can be applied to figure out whether the query, which in the recommendation case could be just, the product detail page that they are on, plus some other products that they have seen in this context, plus their historical behavior, right? So the query could consist of a bunch of those things plus the business context. And typically what happens is the richest models, or the most complex models, what they do is they take a document is nothing but a product. So they think of a document, which is all these blue rectangles, as multiple tokens in the product. Think of this as each word in the product description, each word in the title, if you will. And a query is, again, each word in the title of the product on detail page on which the user is. Let's just keep it simple. And then what you obviously heard of transformers, and attention is all you need, paper, and that's really what's happening. Every token is interacting with every other token and influencing it. And this happens, multiple times. The first time, the second time, more, third time, and so on and so forth, until you kind of get to a point where you have modified each token based on the other tokens, right? So it's an n squared thing going on. So each token is getting modified by other tokens, and then net at the end you'll compute what's called a similarity score of all these resultant tokens that are at the top. Okay, so something that's called BERT. Now it's obviously, as you can see, it's a pretty expensive process. Okay, so you're doing a lot of work during inference time. Now, of late, there have been some suggestions where you say, look, let's try to pre-compute some things. You don't have to compute everything at inference time. Can we pre-compute some things? So what does that mean? Well, if something is not changing at query time, if something is static, those interactions need not be computed again and again during query time. So for example, the interactions between the document tokens is something that is independent of the query. And so you can compute those interactions sort of ahead of time, okay? And the query interactions are also computed as soon as the query comes. And then there is a much simpler algorithm that takes these query tokens and document tokens, which are already sorted out the interactions amongst themselves, and puts them together. Okay. Now, obviously, it's a simpler algorithm, but there's a cost. What is the cost? The cost is the amount of data you have to store, the number of features that you have to store. You might look at this picture and say, hey, look, wait a minute, there's the same number of rectangles. Why is there more here to the right, to the left? That's a subtle point. And the reason is these tokens are just the number of tokens in the entire corpus. This is the word, jeans. This is the word Nike. This is the word blue. And there are so many, thousands of words, and you need embeddings for those thousands of words. So it's fairly well contained in terms of memory and data size. Whereas here, there are all kinds of combinations of words corresponding to each product. And what you have to store, the top four here, are the interactions of those combinations. So those interactions are plenty. So you're going to have many such distinct features, if you will, I call them feature crosses, because that's really what's happening. And these feature crosses are going to have to be stored in the database. And if you want to sort of, when you want to score this document or re-rank this document, you're going to say, hey, fetch me these features that are sitting right at the top, which are very distinct from features that are for some other document, which are very different from some other document. And so you're going to have to get these features. And if you assume there are 100 tokens for a document, then 100 features that are very specific to this document need to be fetched. Okay, and then it needs to be interacting with the query and then output. Although I kind of gave this example in terms of text, it generalizes. I mean, you've probably heard of recommendations in the context of deep and cross networks, DCN, V2, and so on and so forth. But it's the same sort of things. I mean, whatever it is, there are some signals, some features that are not dependent on the current session or the current day, if you will. They're kind of historic information. So you can pre-compute those crosses. And there are some things that you can't pre-compute. And whatever you can pre-compute, you should, because that accelerates your machine learning inference, provided you have a turbocharged database behind you. So that's the key, right? So you can pre-compute, provided your database can deliver them fast and furious. And that's really what Aerospike does. Okay, we'll double click on this a little bit more. Here is a slightly alternative view of trying to understand what I just said. And this actually goes back to the statement that you heard from the Myntra data scientist, which is they said, look, other databases could not get me back the data that I wanted in the time I wanted it. So let's say, there is a feature store that takes, let's say, 8 milliseconds, as they said, 8.5 milliseconds to retrieve things. And let's say we take 0.8 milliseconds. So, I mean, I'm not great at scale, but let's pretend that this is 1/10 of this, okay? And let's pretend that the entire budget you have is 50 milliseconds. So notice that by dramatically contracting this feature store width in the Aerospike case, this is the Aerospike database, I'm able to give back more time to the modeling steps. And in fact, in our 4-step model that we had, with Aerospike, I can complete all 4 steps. And not only that, I can complete it by getting more data out of the feature store to boot. So not only that, the height of these rectangles are higher than the height of these rectangles. So net, if you compute the area under the blue rectangles, which is really in some sense representative of how much work the machine learning inference can do, it's way more than the area under these 2 blue rectangles. So you can not only do just two steps, you can get less data here. And so this is fundamentally the reason why Aerospike is the preferred choice when you're doing predictive AI in general, and in recommendations in particular, as we talked about just now. So let's look at another quote from somebody at Rakuten. Similar thing, for each machine learning model for recommendation, Aerospike can double or triple the data we have, and no other database was able to accommodate it at that speed. That's the quote from Rio at Rakuten. Okay, I'm going to quickly sort of talk about our present slides of our customers in their own original format, and just maybe hit upon a few points, and we'll conclude and we can take questions. So Myntra uses us for personalization or recommendations on their e-commerce website. They're a fashion e-commerce website. Essentially, as you can imagine, there is a home page, there is a search and list page, there is a product detail page or a product display page. And in each of these places, there is an opportunity to put recommendations or suggest recommendations, and that's exactly what Myntra does. Not only that, Myntra also uses us in the context of a conversational shopping assistant called Maya, where you can have an ongoing conversation, and the agent has to remember exactly what you said before, not lose the context. In your 4th question, it should not come and ask you again, what you did, what you really wanted when you had already said it several minutes ago. So the context during a chat is stored in Aerospike. Of course, the underlying engine that the conversational agent is talking to is the recommendations engine, which is also based on Aerospike. Okay. So I think the main point I'm going to sort of talk about here is that um, they really were very fixed on this model prediction time being very fixed, and so they needed to optimize on the feature lookup time. And they were evaluating between Aerospike and Redis, and first of all, they found that Aerospike had even better sort of latency than Redis. But more importantly, it's the cost, okay? Because almost 1 terabyte of features had to be stored in memory for Redis, whereas that could have been kept in SSD for Aerospike. So you produce better latency for a lower cost, and that's really the compelling value proposition. Sony is another example. Again, feature store requirements, 100 plus million users, 5 terabyte of storage, less than 10 millisecond data retrieval, low TCO, right? So that's what they wanted. And they did a bunch of analysis, compared Aerospike to Couch to Cassandra. And if you notice, in terms of resiliency and TCO, we were far superior, and obviously sharding was automatic. And so net, they ended up using Aerospike. Wayfair went through a similar journey. They were trying to sort of find something to replace Redis with that was low latency, reliable, scalable, manageable, and where they could sort of depend on us, their partner, to support them. And they were using Cassandra before, and the complexity was derailing them around operations and performance, tuning the JVM constantly, and the number of the server sprawl, the latency that you could get. So they introduced Aerospike and brought 60 servers down to 7 servers. And then they kind of computed the cost per usable terabyte, taking the whole holistic cost analysis, the cost of the hardware, the cost of licensing, and other OpEx costs, the operational costs, and so on and so forth. And it was a no-brainer for them. And finally, they said, look, you guys are a huge partner for us, and repeatedly you were able to bail us out if there was ever a challenge. And these are all slides of our customers that I'm reporting directly. So I'm going to pause and tell you that, hey, here are 2 useful resources that you can look at. You can click on the QR codes or take a picture of the QR code and get more information, and then point you to the fact that there is going to be a series of workshops that we're going to be conducting at several cities across this next few months. These are going to be, hands-on workshop, and again, you'll find more information when you click on this or when you scan this QR code. Okay, thanks. That's it from me, and I will take questions at this point of time. Thank you.